Okay, so let's pick up where we left off. Here are the air pressures, and I'll just write in the values. So here we had 29.44 inches of mercury, 1,021 millibars, 29.71 inches, 29.0, 1,000, 1,023, and 30.09. Okay, so those are the air pressure conversions. Just use the chart in the reference table. I think it should be okay. Straightforward. Now we get to changes in atmospheric pressure. Not as straightforward. The atmospheric pressure is not constant. It can change. And it changes due to primarily three factors. One being temperature. The temperature of the air is going to affect atmospheric pressure. Humidity, moisture, is going to affect air pressure. And then lastly, altitude. Okay, so these three things will affect the atmospheric pressure. Now, if we look at each one individually, well, the first two especially are a little more complex than it might seem. So if we take a look at temperature first, one of the things that's a little confusing about this is there's two ways we can think about it. If we think about, say, something like a bottle, I don't know, maybe something kind of like that. Let's say that's my bottle, and let's say I have the cap on it tight. So we've got a sealed bottle. And if I increase the temperature, the pressure inside the bottle is going to build up in all directions. If I heat the bottle up enough, it might break, it might explode, it might burst. The atmosphere is different though. The atmosphere is not a sealed bottle. There are no walls to the container, there's no sides. In the atmosphere, it's basically infinitely open. There is no sealed box or bottle or container. So in this situation, it's different. For the atmosphere, when the temperature increases, the particles move faster, the particles of air move faster and away from each other. And since they're moving away, they're getting spread out. This can't happen in the bottle because the bottle is holding everything in place. But without a bottle, the hot air particles start moving faster and they start moving away from each other and they start spreading out. And if the air is more spread out, it's less dense, which means there's less pressure. So if we're talking about the atmosphere, an increase in temperature is actually going to correspond with a decrease in air pressure. This is opposite the bottle. It's different because there's no walls to a container. It's not being held tightly in one spot. It's not locked in a box. And because of that, when the temperature rises, the warm air can spread out more. It's less dense, so air pressure goes down. Colder air has a higher air pressure because the air is more dense, it's more compact. The particles aren't trying to move away from each other. So this is one thing that can be a little tricky about the relationship between temperature and air pressure. I've had students in the past that were thinking along the lines of a sealed bottle, but it doesn't work that way because the atmosphere is not a bottle, it's not a container, it's not sealed. It's all open, and that air can really spread away in a way that it can't inside of the bottle. So that's the first relationship. The next one is moisture. And moisture can be a little tricky too. So moisture or humidity will affect the air pressure. Now, what this diagram is trying to show up here, and I know it's difficult to read, but we have nitrogen gas, I'll put an N, oxygen gas, carbon dioxide, CO2, and H2O, water vapor. Now, what this little chart is trying to show, and it's, again, too small to really see well, but if we actually were to weigh these different gases, if we were to compare them in an equal way, if nitrogen, say, weighed 28 grams, oxygen is going to weigh 32, carbon dioxide 44, and water vapor 18. The elements have different weights. Remember, the electron has really no mass. The mass of the atom is in its nucleus. And when we look at the nuclei of nitrogen, oxygen, and the combined nuclei of carbon and the oxygens put together, these are the masses that we come up with. Water vapor is much lighter than nitrogen and oxygen. Hydrogen and oxygen, this is lightweight material. So what that means is that in normal dry air, without a lot of water in it, we have it made of nitrogen and oxygen, maybe a little bit of carbon dioxide too. But it's dense. The mass of nitrogen, the mass of oxygen is high. But if we take that dry air and we add in some water, we replace water vapor molecules, replace air molecules, essentially nitrogen and oxygen. So the water pushes out nitrogen and oxygen. And again, remember, this is not a sealed bottle. This is the atmosphere. It's open. It can go and spread itself out in all directions. So when we introduce some water vapor through evaporation, we're displacing heavy nitrogen and oxygen out of the way. And that has an overall effect of making the air lighter. So humid air is actually less dense. It weighs less for the same volume. Dry air always weighs more. Humid air weighs less when we're comparing equal quantities. And it's because we're pushing that nitrogen and oxygen out of the way. It's not that the nitrogen and oxygen disappears. We've just displaced it to somewhere else. Now, occasionally somebody will ask me, well, why is it that humid air feels so heavy? You know, in the summertime, July, August, maybe even June, the air feels so heavy when it's really humid. It's actually not. It's actually less dense. But we do feel uncomfortable when the air is humid. Sorry. Uncomfortable. We feel more uncomfortable. Getting a little tired, it's getting late. But we feel more uncomfortable when the air is humid because evaporation is less effective. Remember, evaporation works better in dry air, and when the air is humid, the air can't absorb as much water through evaporation. What this means is that you don't sweat as well. So sweating doesn't work. Or I'll say it doesn't work well. You know, if you think about times where maybe you've been in gym class and you're drenched in sweat, it's probably a humid day. You know, on a hot, humid day, you're going to be sweating, maybe even just going up the stairs or doing something really not that hard. Whereas in the wintertime, it takes a lot more to get you to really sweat. In the wintertime, because the air is dry, any sweat that you produce is evaporating off your body right away. When the air is humid, because evaporation isn't working as well, that sweat is not going away and is running down your face. It's going into your eyes, running into your eyebrows and everything, because it's just not evaporating. Because the air is humid, the air is already holding a lot of water. So this is kind of counterintuitive. It's not what most people would expect. Most people would expect dry air to be less dense and humid air to be more dense. So the effect when we're talking about pressure is directly related to density. So as humidity increases, air pressure decreases. Air pressure actually goes down. So air pressure decreases as humidity increases. Again, we're pushing the nitrogen and oxygen out of the way, replacing it with lighter weight water molecules. That lowers the density and lowers the air pressure. So in this case, our graph is going to slope down like that. Now, lastly, we have the effect of altitude. Altitude is a little bit more obvious. As we get higher in altitude, there's simply less air as we go higher up. So we have low pressure at higher elevations, and we have higher pressures. Well, actually at the top of a mountain, it would be like kind of a medium pressure. A place like Denver, Colorado, you might actually feel that air pressure difference, the mile-high city. When we get down to sea level, which is essentially where Goshen is at, we have high air pressure, around 1,000 millibars down there, around 1,000 millibars. And again, it's just simply there's less air the higher up you go. The closer you are to the ground, the more air there is. So there's a greater density of air, greater air pressure. As you go higher up, there's less air, lower air pressure. Okay, so with this last relationship, we could say as altitude increases, as altitude increases, air pressure decreases. Okay, which means that our graph in this case is going to go in this direction. And you have a chart like this in your reference table that you should be familiar with. I don't remember what page it is off the top of my head, so you should get your reference table out and take a look at this. But it's showing the different layers in the atmosphere: troposphere, stratosphere, mesosphere. One thing I think I forgot to mention that day we talked about this is the boundary between the troposphere, stratosphere would be called the tropopause. And then in between the stratosphere and mesosphere would be the stratopause. And then between mesosphere and thermosphere, mesopause. Okay, it's just the boundary between them. And this line graph is showing the drop in air pressure. So as we get higher in altitude, the air pressures are dropping off rapidly. Okay, I think I'll just do one last quick little video to wrap up air pressure, maybe about 5 minutes, and then that should be it for atmospheric pressure.